Hello everyone, welcome to the review for the second exam for our Introduction to Statistics course. On the screen here, you can see the formulas that we are going to supply for you for the exam. So from Chapter 3, which is on Introduction to Probability, we have our multiplication rule for probability for two scenarios where A and B are independent and where A and B are dependent. So when they are independent, then the probability of A and B is just equal to the probability of A times probability of B. If they are dependent, then it will be the probability of A times probability of B given A, or the probability of B times probability of A given B. We also give the addition rule for probability for both when A and B are mutually exclusive and when they're not mutually exclusive. So if they are not mutually exclusive, we have that the probability of A or B, which is the union, will be the probability of A plus the probability of B minus the probability of A and B, right? Because you have everything from A, everything from B, and then you also have to take into account you double counted that intersection, so you have to subtract that piece out. If they are mutually exclusive, we have the probability of A or B equals probability of A plus probability of B, which it's really the same thing as the other formula, except for the intersection ends up equaling 0 because there's no intersection, meaning that there is no, it's the empty set. So therefore, probability of A and B equals 0. Then we have the formulas from Chapter 4, which cover discrete probability distributions. So for any discrete probability distribution, no matter what it is, we can always find the expected value of our distribution, which is equal to the mean, by taking every value that we have, x, and multiplying it by its associated probability, x, so px. And this goes based on the definition of a probability distribution, which is where we have every possible outcome and its associated probability. If we are looking for the variance, we are going to take that mean that we found, or expected value, we're going to subtract it from every value we have, that's the x minus mean, mu, and we're going to then square that so we get rid of any of the negatives, and we're going to multiply that by its associated probability, p of x. We'll take each of those values and we'll sum them up. And then of course, if you want the standard deviation, you're just going to take the square root of this entire thing. But sometimes our discrete probability distributions are going to have too many x values for us to figure out what all the actual individual probabilities are. So this is when we're going to use our probability mass function, which is actually a function which describes the probability based on any possible value from our random variable. So let's say we have a random variable x. Then even if we have some discrete probability distribution where we have an infinite number, right, a countably infinite number of values, this function will describe every probability that is possible associated with every possible value of our random variable. So for binomial distribution, which isn't countably infinite, but it could have a lot of tedious calculations to do, we have that our expected value, or our mean, is equal to n times p. So the number of trials times the probability of success. Our variance is going to be n times p times q, and our standard deviation would then be the square root of n times p times q. And we also supply, for the binomial probability distribution, the formula, which is just going to be n choose r, p to the r, 1 minus p to the n minus r. Now in our class, we have covered other distributions, for example, like the geometric probability distribution, which is countably infinite, which is where these expected value, variance, and standard deviation shortcuts are really useful. But in this case, we're only going to be having binomial on the test. Geometric will be on the next one. Now for our exam, we're going to start with a lot of concept questions. These will be more fill in the blank, true or false, things like that. But on our practice exam, we're going to do a little bit more open-ended concept questions. So the first one says, what two conditions must a discrete probability distribution satisfy? Now, this is for any discrete probability distribution, and the two features that they have to have is that all of your probabilities, probability of x, must be between 0 and 1 inclusive, and if I were to sum up all of these probabilities, they would have to make up the entire sample space, so therefore the probability of all of these added up together must be equal to 1. This is different from when we do a continuous probability distribution, specifically for this key second step here, the sum of all the probabilities. Because when we have continuous data, we cannot sum an infinite number of possible values, so we actually have to use a slightly different method. But this first part, this probability between 0 and 1, is going to be true for any probabilities that we have in any probability distribution. Second question asks, what does the mean of a probability distribution represent? So this is going to be your expected value or your average outcome that you would expect if you were to repeat this over and over and over again. So this means that if I'm doing a binomial probability and I'm flipping 10 coins, the expected value is going to tell me how many coins I would expect to be a success, let's say landing on heads, if I were to repeatedly flip these 10 coins over and over again. So it means that while the value may deviate from that expected value, it is the average of me repeating this experiment over and over and over again as n approaches infinity. So basically what it's saying is as n approaches infinity, then my expected value is just going to become the mean of what my outcomes are. Meaning that, for example, if my expected value is 6, I might have values of 5, 4, 7, 9, 2, 6, 4. But over time, it's going to average out to this expected value, which is the mean of the outcomes from this repeated many, many times as we repeat this trial over and over and over again. Part 3. In a binomial experiment, what does it mean to say that each trial is independent of the other trials? So if you remember from probability, independence means that if I have the probability of some A given B, then this will be equal to the probability of A. And all this means is that given some B has occurred, this does not impact the probability of A, so it is just the probability of A. More specifically for the binomial probability distribution, this is because we have the constraint that P is constant. And for P to be constant, this means that my probability cannot change between trials, meaning that if I am pulling a card from a deck of cards, let's say I'm looking for a face card, and I'm going to draw the card 10 times, I would have to do this with replacement because if I were to draw a card, let's say it's a 2 of clubs, and I took it out of my deck, that means now when I draw that second card, I've changed the probability, which would mean that it's not constant. So I would have to do it with replacement. I'd have to take that card, put it back in the deck, which means that my probability does not change. That means that the card that I draw on the second draw is not affected by the first draw. So being independent means that any probability that I find will not be affected by the other events that occurred before it. Part 4 asks, in a binomial experiment with n trials, what does the random variable measure? So the random variable will measure the number of successes. So if you remember, when we have a binomial distribution, we have our binomial and we have 2 parameters that we need to know. We need to know what n is, the number of trials, and we need to know the probability of success. And with those 2 parameters, that locks us into a particular binomial distribution. And from that, we can figure out the number of successes R, or you might choose to use X, that's perfectly fine. So it's the number of successes. This is what we're actually looking for when we do a binomial probability distribution. So our random variable for a binomial probability distribution is the number of successes. And this can be, so this would be number of successes, and this can be any value from 0 successes, 1, 2, ... up to a total of n successes. Meaning that if I'm flipping a coin 5 times, I could get 0 heads, or 1 head, or 2 head, or 3, 4, or up to the total of 5 heads, again, because I flipped the coin 5 times. So your random variable for a binomial probability is how many successes you have. Problem 5 says, given the odds are 7 to 2, so we have the odds of E are 7 to 2. This is, remember, odds are successes to failures. We want to know, first of all, what is the number of our total sample space? So in this case, you just take these 2 values, you add them up together, 7 plus 2, and we get a total of 9. Part B asks, what are the odds of the complement of E, or not E? Well, for this, all we're going to do is, in this case, we're considering the event we're looking for as the failure, so we would just flip these 2 numbers, so this becomes 2 to 7. And you can think of this as, when we do the odds, as wins to losses, right? If I were to say that I had odds of 7 to 2 for 2 football teams playing against each other, it means that if they were to play 9 games, I would expect this team to win 7 games and lose 2 games. The odds against this, which would be the odds against the team, would be 2 to 7. I would expect them to lose 2 games and win 7. Part C asks, what is the number of the complement of E? So that is actually just going to be this number. We have the odds of E, it's your second number, or in this case, the odds of not E, it's your first number. It's the losses. So this is going to be equal to 2. And then D is what is the probability of our event E. And if you remember, the probability is just the number of outcomes in E divided by the number of outcomes in our sample space. Well, just like we found the number of outcomes in our sample space, if we think of this, our odds, this is the number of outcomes E, and this is the number of outcomes not in E. So the number of outcomes in E, in this case, is going to be 7 divided by the total number, which is going to be 9. Our next question asks, if events A and B are dependent, then the probability of A and B is equal to what? And it's specifically asking for the formula. So if you remember, the probability of A and B, so the probability of A intersection B, that's our intersection symbol, it's going to be thought of as an AND symbol, is going to be what happens to the probability of A times B if they are dependent on each other. So this is just going to be either the probability of A times the probability of B given A, or it could be the probability of B times the probability of A given B. And this could be, for example, if we were to consider a Venn diagram with A and B, then what we could have, for example, the first one is the probability of getting A. So this would be this probability of getting one of these events. And then given that I have A, what is the probability that I get something that is B? Or similarly, we could have the opposite, which is, again, if we have A and we have B, it is the probability of getting something in B. And then given that B has occurred, what is the probability of getting something that is in A? So the intersection is just what they have in common. So the way we can find it for probability of A and B is probability of A times probability of B given A, or probability of B times probability of A given B. If this question were flipped and it was saying that they were independent, in which case if they're independent, this means that the probability of A given B would just be the probability of A, then in this case, the probability of A and B would just be the probability of A times the probability of B. And this is because if we were to look at these, probability of B given A would just become probability of B, and probability of A would just become, probability of A given B would just become probability of A. So if they're independent, this means that it would be just probability of A times probability of B. Now this question did ask saying that they're dependent, meaning it would be one of these two answers for the formula. Question 7 says, let E be some event and E complement be the complement. Then the probability of E and not E is equal to what? So if we take the probability of E and not E, or the intersection, we have to now consider what this could be. So again, I'm going to draw a Venn diagram, and let's say that we have our event E. So this is E. Then not E is going to be everything that is not in E. So based on this question, probability of A and not E is going to be equal to the probability of the empty set, because they have no overlap. They don't share anything. They are mutually exclusive. This means that the probability will be equal to 0. Now, there's a couple variations of how we might ask this sort of question. For example, what if instead I had asked you for E and not E? In this case, I'm asking about the set, in which case they have nothing that they share in common, so this would be the empty set, which you can either write as open curly bracket, close curly bracket, or you could do this symbol for the empty set. Another question we could ask, instead of asking what it is if we take the intersection, what if we said the probability of E or not E? And then similarly, what is E or not E? Well, if I look at this Venn diagram here, if I looked at E, something that is in E or not in E, then I'm going to get everything. So this is just going to be the sample space. So the probability of E or not E would be the probability of getting the sample space, which would be equal to 1, because they account for every possible value, and there's no overlap, so we don't have to worry about subtracting the intersection. So this is pretty much all the variety of questions we could ask like this. So this is the one thing you need to be careful with this, though, is because if we ask about E and not E, this is the set, meaning it is the empty set. If we're asking about the probability of E and not E, this is the probability, which has a value between 0 and 1 inclusive, meaning that it is 0. Same thing here. If we ask about E or not E, this is the sample space because it is all the possible values. If we ask about the probability of E or not E, this is the probability, which again has to be between 0 and 1 inclusive, which is equal to 1. The next question asks, what is the number of 5-digit codes that are possible with repetition of digits if the first digit must be odd and the second digit cannot be 0? So in this case, we have 5 digits, 1, 2, 3, 4, 5. And we want to know how many possible digits, combinations we can make with this. So it says with repetition. That means that every single step, I can use a number that I've used before. So for example, if I use a 5 in the first value, I can use a 5 for the others. One of the other variations you might get on a problem like this is we say without repetition, in which case once a value is selected, you have one less value to select for the next value. Now it does have the restriction that the first digit must be odd. So therefore, if we look at our odd numbers, we have 1, 3, 5, 7, and 9. So we have 5 odd numbers. So these are the values that we can choose from. Now, for the second value, because we have repetition, let's say we chose one of these 5 values. We still have access to that for the second value. We do have another restriction, though. The second digit cannot be 0. So now we have to consider how many other values there are. Well, I can still get 1 through 9, which means I have 9 possible digits to choose from. Going to the third digit, there are no restrictions. That means everything's available for me to use. So therefore, I have the values 0 through 9, which means I have 10 values. For the fourth one, I have 10 values. And for the fifth one, I also have 10 values. So then for the total number of digits, we have 5 times 9 times 10 times 10 times 10, which is just going to give us 5 times 9 times 10 times 10 times 10, gives me 45,000 possible values that I can get with these restrictions. The first number has to be odd. The second number cannot be equal to 0. And then the rest can be any value, and this is with repetition. Question 9 asks, if A and B are not mutually exclusive, then probability of A or B is equal to what? So in this case, it's just going to be the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And this is because if I were again to draw a Venn diagram, I'm looking at everything in A. I'm looking at everything in B. But I've double counted the center part, so I have to subtract out the intersection. If they were mutually exclusive, this would then become probability of A plus probability of B minus nothing, because when they're when they're mutually exclusive, this term goes to 0, so therefore it just ends up being probability of A plus probability of B. For our next question, it says, in a data set where the distribution is approximately symmetric and bell-shaped, blank of the data will lie within 2 standard deviations of the mean. So this problem is just a quick, simple empirical rule problem. And if you remember, our empirical rule says that if we have bell-shaped and symmetric data that is centered at the mean mu, that if we were to go out -1 to +1 standard deviation, this will account for 68% of our data. If we were to go out 2 standard deviations from the mean, this would account for 95% of our data. And if we were to go out -3 standard deviations to +3 standard deviations, this would account for 99.7% of our data. So in this case, because it's asking about 2 standard deviations, the answer is just going to be 95% of the data should fall between these 2 standard deviations. Now remember, this is specifically for if you have perfectly symmetric bell-shaped data, the more it deviates from that normal behavior, this is going to deviate a little bit from there. Remember, we talked about this in our class where we also had Chebyshev's inequality or Chebyshev's theorem, which gave us a minimum amount that should fall within some number of standard deviations with some other restrictions, but it worked for any distribution. Some other factors about this, though, is remember we talked about this in class that we could always figure out how many are within the subparts of this by, for example, taking the fact that if 68% are between negative standard deviation and positive standard deviation, if we took half and half, this would be, of course, 34% and 34%. You could do the same thing with these, taking into account that you've already accounted for 68% of the data. You have 95% of the data from here to here, which is whatever's left here is 27%. So this would be 13.5 and 13.5. And then same thing here. This would be 2.35, I believe, 2.35. And then, of course, the part that's left for the outer part is only 0.3%. So this then would be outside would be 0.015, and this would be 0.015%. So you can actually get quite a bit just from the simple fact of within one standard deviation, 68%, within two standard deviations, 95%, within three standard deviations, 99.7%. In this, I used mu and sigma to represent my mean and standard deviation. This also can be true if you have sample data. So this could have been X bar and these could have been S, right? Plus or minus S. This works just as well as long as it is bell-shaped and symmetric. For the next part, we have some true or false questions. Now, generally what you're gonna need to do is on an exam, you'll just put true or false. You don't really need to justify it. But we're going to be looking at it to fix it if we have a problem while doing the review. So the first one says, in most applications, continuous random variables represent counted data, while discrete random variables represent measured data. So this is false, and pretty much what this means is just we're gonna flip them, right? So discrete data is counted data. Usually it's going to be something you counted, right? You go through and you're gonna get the number of cars in a parking deck, the number of phone calls in a day or a given hour, things like that. Whereas in continuous random variables are measured variables because they're based on intervals. Number 12 says the expected value of a random variable can never be negative. So this is false. An example of this would be when we did something like the raffle ticket example in class, or think about any time you go gambling. Any game that you go play at a casino, your expected value as the player will be negative because this is how casinos make money. They know the probabilities of every outcome for different games, and they have the rules set up so that they will have a positive expected value, meaning that on any given game, you may win or lose. You may win a lot of money, you may win a little bit of money, but they know that given enough games, right, law of large numbers, that the empirical probability will approach the classic or theoretical probability. And that means that they know that given enough games, it will approach what is the expected outcome. So they have a positive expected value, meaning that they expect to make a certain amount for every bit of play based on a game. You as the player have a negative expected value. You are going to lose some amount over time on average for every game. Now, of course, in any given game, it doesn't mean that you're going to lose, but it means that over time, if you were to play for an infinite amount of time, you would have an expected amount that you would lose per hand or game that you've played. Number 13 says, the mean of a random variable of a probability distribution describes how the outcomes vary. So this one is clearly false because the mean, which is the expected value, is the average of the values if you were to repeatedly do the trials or experiment. So what describes how the outcomes vary would either be the variance or the standard deviation. So in this case, the mean of a random variable for a probability distribution describes it describes the average or the mean of the data. Okay, now we're done with our concept questions. It's time to move into some actual calculations. So the first set of questions, number 14, is using a deck of cards. So a card is selected at random. What is the probability the card selected is either a queen or a black card? So we want to know what is the probability of getting a queen or a black card. So if you remember, the union of two events would be the probability of getting your first event, probability of queen, plus the probability of getting a black card minus the probability of getting a queen and black card. So in this case, we have to look at what is the probability of getting a queen, right? And if you remember, our basic probability is that the probability of some outcome A is just the number of outcomes A divided by the number of outcomes in the sample space. So for queens, there are 4 queens in the deck: queen of hearts, queen of diamonds, queen of spades, queen of clubs. And there are a total of 52 cards in our deck of cards. Now let's look at the black cards. There are a total of 26 black cards. This is because there are 13 clubs and there are 13 spades. So a total of 26 black cards, or half of the cards. And then we need to subtract the probability of getting a black queen. So there are 2 black queens, the queen of spades and the queen of clubs, out of our total 52. So this is going to be 4 plus 26 over 52, which is 30 over 52, minus 2 over 52 is going to give us 28 over 52, which of course, if we wanted to simplify this, this would be what? 14 over 26, so 7/13, which I'm just going to write down the decimal real quick. So this is going to be 28 divided by 52. I get 0.538. The second part of the question asks, if 2 cards are drawn in succession without replacement, what is the probability both cards are black? So this means that we want to find the probability of getting a black card. I'm going to put B1 just to help you keep track. And then a second black card. Now you don't have to put these subscripts. It's just the probability of a black card and a black card. So what we're going to do is we are going to take the probability of getting our first card being black times, because this is multiplication, we're going to use our multiplication rule. This is going to be times the probability of getting our second card being black, given that the first card was black. So in this case, how many black cards are there in a deck of cards? Well, we just talked about it in the last problem. There are 26 out of 52. And then for our second draw, because we drew out that black card, if this occurred, and we put that aside, that means we have 1 less black card in the deck, meaning now we have 25 out of 51 total cards. So if we were to then multiply this out, we get 26 divided by 52 times 25 divided by 51, and I got 0.245. Now, one thing I do want to point out whenever we're doing this is that if you ever are doing a conditional probability of B2 given B1, this is under the condition that B1, the probability of B1 is not equal to 0, right? Because remember we talked about the fact that if I have the probability of A given B, this is the probability of A and B divided by the probability of B. So in this case, probability of B cannot be equal to 0, which kind of makes sense intuitively, because if you think about it, how can I have the probability of getting a second black card given the first one was black if I could not have gotten the first black card? And this is what this is saying. If my given initial condition could not happen, then how could I get something based on that initial condition happening? So the next problem says, find the probability of drawing a jack that is red or a queen. So in this case, we want the probability of getting a red jack or a queen. So just like before, this is going to end up being the probability of getting a red jack plus the probability of getting a queen, and then of course minus the probability of getting a red jack and queen. Now you may have noticed that there is no card that is both a red jack and a queen. So if you had noticed this, you could have actually considered that they are mutually exclusive, and you could have left this term off, because this is just going to go to 0. So first thing we're going to do is we need to figure out what is the number of red jacks. Well, there's 2 of them. There's the jack of hearts and there's the jack of diamonds out of our total 52 cards. Plus, what's our probability of drawing a queen? Well, there's 4 queens: queen of hearts, queen of diamonds, queen of spades, queen of clubs, divided by 52. So this is just going to be 6 over 52, which will equal to 3 over 26, or 0.115. For our next problem, it says a six-sided die is rolled 80 times and the number of times each number showed up and their probabilities are given below. We want to complete the table with the probabilities, and then we want to find the expected value and the standard deviation. And then part C, it asks, is this a probability distribution? Why or why not? So first things first, we want to consider that we have a total of 80 dice rolls. And we got 12 ones, we got 22 twos, 9 threes. We don't know how many fours we got. We got 7 fives, and we got 18 sixes. So in order for this to be true, it means that this last one has to account for whatever is missing from these 80 dice rolls. So all I'm going to do is I'm going to add up these numbers and then subtract it from 80. So I have 12 plus 22 plus 9 plus 7 plus 18, and I got a total of 68 dice rolls. So then I just subtract that from 80, and I get a total of 12. And now I need to figure out what is the probability of each of these outcomes. Well, the fact is that I've got 12 out of my total 80, so this is just going to be 12 over 80. This is going to be 22 over 80. This is going to be 9 over 80. This is going to be 12 over 80. This is going to be 7 over 80. And this is going to be 18 over 80. Now, when doing these calculations, a lot of times people like to round these into decimal value. That's perfectly fine. For example, if I took my 12 divided by 80, I would just get a value of 0.15. So I'm just going to write these below in case anybody wants to follow along and do the calculations using decimals. So this is 0.15. This one is 0.275. This one is 0.1125. Oh, we already had this one, 0.15. 7 divided by 80, 0.0875. And then 18 divided by 80 is equal to 0.225. Now, I'm actually going to jump ahead real quick and look at part C. Is this a probability distribution? Yes or no? And the answer in this case is yes, because does it include every possible outcome? Well, if I roll a six-sided die, my outcomes are 1, 2, 3, 4, 5, 6. And do I have their associated probabilities? 0.15, 0.275, 0.1125, 0.15, 0.0875, 0.225. Yes. And then we have some certain properties that have to be true, though. If I were to sum up these probabilities, right, because I know that I got them by counting these numbers that account for all 80, they would have to sum up to 1, which 12 over 80 plus 22 over 80 plus 9 over 80 plus 12 over 80 plus 7 over 80 plus 18 over 80 would be 80 over 80. So the sum of these probabilities do account for all of the possible outcomes. So yes, this is a probability distribution. Okay, so now what we want to do is we want to find the expected value and the standard deviation. So the expected value is going to be the sum of all of our outcomes times their associated probability. So this is going to be equal to, now remember, the outcomes are the x values. Once you've got the probabilities, you no longer need this count information. So don't worry about that anymore. So we have 1 times a probability of 0.15 plus 2 times a probability of 0.275 plus 3 times a probability of 0.1125 plus 4 times a probability of 0.15 plus 5 times a probability of 0.0875 plus 6 times a probability of 0.225. And if we were to put this into our calculator, we would get 3.425. So for the next thing, we want to find what is our standard deviation. So our standard deviation, which is just going to be sigma, is going to be equal to every x value we have minus the mean mu, and then we are going to square that. We're going to take that value and we're going to multiply it by the probability of x, and then we're going to take the sum of this entire thing, and then we will take the square root of that. So pretty much what we're going to do is we're going to take 1 minus 3.425, square it, times probability 0.15, plus 2, so we're going to do that real quick. So give me a second and I'll get that set up. Okay, so now we have this. We have each of our values, outcomes, 1 minus our mean 3.425 squared, times the probability of getting a 1, 0.125, plus 2 minus 3.425 squared, times its probability of occurring. And then we do this for each of them. And then because we're taking the standard deviation, we take the square root of the entire thing. If this were a variance, we would just do the same thing, but without the square root. So generally what students are going to do is they're going to figure out what each of these values are. 1 minus 3.425 squared, and then maybe they multiply it by 0.125 and you write it down. And we could do it that way. I'm just going to do it all in one step. So again, I'll be right back when I have the answer. Okay, so quick thing. I actually put all this in, and this calculator can actually not put in something this long. It actually cut off at the 6. So if you're using a calculator like the TI-30X2S, you would actually have to do this in pieces, like I was saying most students will do. If you have a different calculator, you may be able to put this all in as one step. But in the end, we get a standard deviation of 1.794. Now, previously, when we've had a problem like this in this class, what we had everybody do is we had everybody set it up like this, but we didn't have them calculate the final answer, because in the end, if you've been able to figure out what you're solving for, what's your formula, plugging in your values, at that point, all you're showing is that you know how to use a calculator. And honestly, that's the least consequential part of this entire class. Our next problem says, when playing roulette, the probability of winning if you pick a color, which is red or black, is 0.4734. You play 8 games. Can a binomial probability distribution be used to find the probability of winning R number games out of 8? Why or why not? And the answer to this one is yes, because we have a set P value, right? Our P which is our probability of winning, is going to be 0.4734, which of course means that our Q, our probability of losing, would be 1 minus this. We have a set N of 8 games. There are 2 possibilities per trial. The probability does not change. So yes, you could use a binomial probability for this problem. In fact, I actually gave this problem in an exam one time, and this caused a lot of confusion for students. This is based on the actual numbers from Roulette. If you look at an American roulette wheel, there are red numbers, there are black numbers. There are an even number of them, meaning that if you just had the red and black, you would have a 50-50 shot. But a European roulette wheel has a special green 0. The American roulette wheel has 2 green values, 0 and 0, 0. So this actually makes the probability of getting either red or black to be less than 0.5. Remember earlier we talked about how casinos have a way that they have a positive expected value and you have a negative expected value? This is part of it. Because if I were to go and play roulette and I were to just pick a color, it's not going to be 50-50 shot that I win or lose. I will have a probability of winning of 0.4734, which means that I have 1 minus 0.4734 probability of losing. That means that if I lose, the casino gets my bet. Therefore, they have a positive expected value. I have a negative expected value. So the first question for this now says, what is probability you will win more than 2 games? So if we look at what is the probability that I will win more than 2 games? So this, because it's discrete, remember that this is not including 2. So if I were to look at this, this would actually be equivalent to the probability x is greater than or equal to 3. So the question really wants me to find what is the probability that I win 3 games, plus probability I win 4 games, plus probability I win 5 games, plus probability I win 6 games, plus the probability I win 7 games, plus the probability I win 8 games. Now, this is a lot of binomial probabilities to solve. So what I'm actually going to do is I'm going to use the complement, right? Because I know that if I take all the probabilities together, they sum up to 1. So what I can do is I could take the complement of this, which the complement of probability of x is greater than or equal to 3 would be the probability x is less than 3. And if I subtract that from 1, then I will get whatever the probability of all of these are, right? Because basically what I'm doing is this asked me, what is the probability of all these things? So what I'm going to do instead is I'm going to find the probability of this, subtract it from 1, and I'm going to be left with the other side. So the probability x is less than 3 is really the same thing as saying 1 minus the probability x is less than or equal to 2. So really what I'm finding now is 1 minus the probability of getting 0 wins plus the probability of getting 1 win plus the probability of getting 2 wins. This is significantly easier to calculate. So what we're going to be doing for this, we're going to be using our binomial probability, which is going to be, if I have the probability of x, this is going to be n choose x, p to the x, 1 minus p to the n minus x. So in this case, n is 8, p is 0.4734. My probability of failure is 1 minus that, which is going to be 0.5266. And then my x is going to be from these probabilities. So what I'm going to do is I'm going to calculate the probability of getting a 0, a 1, a 2, and then I'll bring it back into here. So my probability of getting a 0 is going to be n choose x, so that's going to be 8 choose 0. Probability of success, 0.4734 to the number of successes power, 0, times the probability of failure, 0.5266 to the 8th power, to the 8 minus 0 power. So probability of getting a 1 is going to be 8 choose 1, 0.4734 to the 1 power, 0.5266 to the 7th power. And then the probability of getting a 2 is going to be 8 choose 2, 0.4734 squared times 0.5266 to the 8 minus 2, or 6th power. This first one is really easy to calculate because remember we talked about our patterns of combinations. N choose 0 will always be equal to 1. Any value to the 0 power also is going to be equal to 1. So this first one is really just 0.5266 to the 8th power. And this gives me 0.0059135. For the second one, 8 choose 8. N choose 1 will always be n. So in this case, this is just going to be 8. So this is just going to be 8 times 0.4734 times 0.5266 to the 7th power. So 8 times 0.4734 times 0.5266 to the 7th power. I get 0.042529. And then for this last one, we're going to do 8 choose 2, which if you use your calculator, remember for a TI-30X2S, you would just put 8, hit the PRB button, go over to NCR, and then hit 2, and I would get 28. Or what we could do is you could solve this by hand. This is just going to be 8 factorial divided by n minus r factorial, which would be 8 minus 2 factorial times r factorial, so 2 factorial. And then what I'm going to do is 8 minus 2 is going to be 6 factorial. Bring that over. Bring over my 2 times 1, that's my factorial. I'm just going to leave the 1 out. And then I'm going to make this 8 times 7 times 6 factorial. The 6's cancel. The 2 cancels a part of the 8, giving me 4. So 4 times 7 equals 28. So there's no reason you can't find the combinations, even if your calculator is not working, you forget it, whatever you want to do. You can still set it up, you can still get this. So this is going to be 28 times 0.4734 to the 2nd power times 0.5266 to the 6th power, and I get that this is equal to 0.133813. Now, if I were to add all these up together, right, because this value is this one, this value is this one, this value is this one. So I'm going to add all these up together, and then I'm going to subtract that from 1. So add all these up. 0.0059135 plus 0.042529 plus 0.133813. I get 0.1822555. Now you might wonder, why am I keeping so many decimal points? Especially because if you look at this, it specifically says 3 decimal points. And the reason is to eliminate rounding error, I keep extra decimal points so that whenever I get to the end, I'll round it at that point, which will help eliminate some of the rounding error. Because if you round to 3 decimals for this, you get 0.006. This one, you get 0.043. For this one, you get 0.334. You've already added a bunch of rounding error. So what I'm going to do is I'm keeping extra and I'll round at the end. So now if I were to subtract this from 1, so 1 minus 0.1822555, I get a total of 0.81, so 77, so I'm going to say 0.818. So my probability that I get more than 2 wins would be 0.818 if I played 8 games. For problem 17, it says a smartphone manufacturer, when receiving shipments of 5,000 batteries, applies the following quality control procedure. They randomly select 30 batteries and accept the entire shipment if there are less than 3 defective batteries in a sample. So if we were to write that down mathematically, they will accept the shipment if the probability of X is less than 3, which of course, because this is discrete data, we can write this as the probability that X is less than or equal to 2. So of course, what are we actually solving for? Using our binomial, because this is going to be one where they either accept it or don't accept it based on the fact of it's faulty or it's not faulty. We're going to be using the fact that the probability of X is equal to n choose X, p to the X, 1 minus p to the n minus X. So because this is going to be a discrete probability distribution, and this solves for the probability of a specific outcome, we can't actually use this formula to solve for this directly. So what we actually have to do is we have to first convert this to what are the actual probabilities we're solving? Well, we're looking at if there are less than or equal to 2 faulty batteries. So that would be the probability of finding 0 faulty batteries plus the probability of 1 faulty battery plus the probability of 2 faulty batteries. And if any of these 3 cases are what they find, they would accept the entire shipment of 5,000 batteries. Part A says, if a particular shipment has a 5% chance of a battery being defective, what is the probability the entire shipment is accepted? And just like we talked about, they will accept it if there are 0 faulty batteries, 1 faulty battery, or 2 faulty batteries. So going back to the original problem, we are checking n equals 30 batteries. And we have a probability of finding a defective battery of 0.05, or a 5% chance for any given battery to be faulty. So now, when we find these probabilities here, we're going to find the probability of 0, we're going to find the probability of 1, and we're going to find the probability of 2. So plugging in our values into our binomial probability distribution, we have n choose X, so 30 choose 0, probability of success, so 0.05 to the X power, so in this case would be 0, and then probability of not finding a defective unit, right? Probability of failure. So this would be 1 minus p, or 0.95 to the n minus x, which in this case would be 30. Probability of 1 is going to be 30 choose 1, 0.05 to the first power, times 0.95 to the 29th power, and then probability of finding 2 defective batteries would be 30 choose 2, 0.05 squared times 0.95 to the 28th power. And now we just need to solve each of these. If you know your combination patterns that we talked about previously, we know that n choose 0 will always be equal to 1. So 30 choose 0 is going to be equal to 1. 30 choose 1, or n choose 1, will always be equal to n. In this case, n is 30, so this is going to be 30. 0.05 to the 0 power, this will also be equal to 1. So for the first calculation, all we actually have to find is we have to figure out what is 0.95 to the 30th power. So we just put in 0.95 to the 30th power, hit enter, and I get a probability of 0.2146. For the second probability, we have 30 times 0.05 to the first power, which is 0.05, times 0.95 to the 29th power. So this is just going to be 30 times 0.05 times 0.95 to the 29th power, and we get a probability of 0.3389. Now for the last one, we can put 30 choose 2 into our calculator. So 30, I hit PRB, go to NCR, and then hit 2, and I get that there are 435 different ways that this could occur. Or what I could do is if I needed to solve this by hand, we know that 30 choose 2 is going to be 30 factorial divided by 30 minus 2 factorial, and then 2 factorial. So what I'm going to do, 30 minus 2 factorial is going to be 28 factorial. So I'm going to bring that over to my denominator. And then at the top, I'm going to put 30 times 29 times 28 factorial. And then, of course, I'm going to put my 2 factorial down here, which is just going to be 2 times 1. So this is going to be times 2, and then times 1. The 1 doesn't do anything. So the 28 factorials will cancel. And then I'm going to cancel this 2 with part of this 30. And I'm going to be left with 15 times 29. Which, if you have to calculate this by hand, like I said before, if you don't have your calculator or it doesn't work or something like that, or you don't know how to find the combination using your calculator, 15 times 29 is a much simpler calculation to do. So we just do 15 times 29, and we get 435. So now back to our binomial probability, 435 times 0.05 squared times 0.95 to the 28th power. So 435 times 0.05 squared times 0.95 to the 28th power. And I get a probability of 0.2586. So now what I need to do is I just need to add up these different probabilities, right? So we have this probability is our probability of getting 0, this probability is our probability of getting 1, and this probability is our probability of getting 2 defective units. We add these together, and we will get that this is equal to 0.2146 plus 0.3389 plus 0.2586. When I add all these up together, I will get 0.8121, which, of course, if we round to 3 decimals, it'll be 0.812. That means that there is an 81.2% chance that if there is a 5% defective battery rate, that they would accept a given shipment when they test 30 of these with the criteria that they will accept it if there are 0, 1, or 2 defective batteries in the batch. If they receive the shipment of 5,000 batteries, what is the expected number of defective batteries in the shipment? And then we want to find the standard deviation of the number of defectives. So because this is a binomial probability problem, we know that the expected value, which is just equal to the average number of defectives you would expect on any given shipment, is going to be N times P. So the fact is we're actually now accepting N equals 5,000 total batteries. So this is going to be 5,000 times 0.05, which is going to be equal to 250. So now this doesn't mean that if you were to accept the shipment of 5,000, you would have 250 defective batteries. This is the average, meaning that if I were to repeatedly accept these shipments of 5,000 batteries with a 5% chance of having a defective battery, that on average, I would expect 250 defective batteries. Now let's see how much this actually varies. So what we're going to do now is we're going to find our standard deviation. So we have sigma, which is equal to the square root of N times P times Q. So plugging in our values, this is going to be the square root of 5,000 times 0.05 times 0.95, and then this will give us our standard deviation. So we take 5,000 times 0.05 times 0.95, and then what I'm going to do is, because I don't like to use the square root function, I'm actually going to use the caret function on the calculator to do this to the 1/2 power, because taking something to the 1/2 power is the same thing as taking the square root. And this is going to equal 15.411, meaning that this is how much we would expect it to deviate. And if you remember from our notes, anything that's outside of 2.5 standard deviations for a binomial probability distribution is generally considered an outlier, meaning that we would probably expect anywhere from 235 to, not 235, we would expect anywhere from about 212 to, I don't know, whatever 15 times 2.5 is. So 30 plus 8, so about 38. So about to 288 is pretty much what we would expect for the normal range of outcomes that we would get based on receiving these shipments. For the next problem, consider a standard deck of cards. We want to find the probability that the card selected is a face card or a heart card. So what we're looking for is we're looking for the probability of a face or a heart. Now to solve this, we're going to be using our addition rule of probability, which is we want the probability of finding a face card plus the probability of finding a heart minus the probability of finding a face card that is a heart. So first things first, what is our probability of finding a face card? How many face cards are there? Well, the face cards are the Jack, Queen, and King. So there's 3 of them per suit, and there's 4 suits, giving us a total of 12 out of 52. Plus, now the number of hearts. There are 13 hearts in a deck of cards, which is a quarter of the deck, right? There's 4 suits, so it is 13 out of 52. You could write this as 1/4, but then it's easier to do the addition and subtraction if they all have the same base. Now what we need to do is we need to subtract the probability of the face cards that are also hearts. And this is because whenever we counted the face cards, we got all the different face cards, including the Jack of Hearts, the Queen of Hearts, and the King of Hearts. When we did the hearts, this also included the Jack of Hearts, the Queen of Hearts, and the King of Hearts, meaning we've double counted that. So we have to look at how many cards are both a face card and a heart, which I just listed them twice, so it's going to be 3. So this is going to be 3 out of 52. So if we look at our numerator of our fractions, right, because they're all the same base, we can just add and subtract them. We have 12 plus 13, which is 25, minus 3 gives us 22 out of 52, which of course would be 11 out of 26, which would then end up being 0.423. The next problem asks us to find the probability that the card selected is an odd numbered card or a prime number card. So we want probability of odd or prime. If we look again at our addition rule, this is going to be the probability of finding an odd card plus the probability of finding a prime card minus the probability of odd and prime. So if we look at which odd cards we have, we've got the 3, the 5, the 7, and the 9. And we have 4 suits of those, so we have a total of 16 odd cards. Now, while I'm writing this down, one thing that I want to point out is to be careful, because if we ever ask you for the number of even cards, you have to take into account that there's the 2, 4, 6, 8, and 10, which means there's 5 per suit for a total of 20. The evens and odds are not the same number, and that's because there is no 1 card. So if you counted the ace, then they would be equal, but because the ace is a special card, we don't count it unless we specify otherwise. So there's 16 total odd cards out of the 52. Now let's look at how many prime cards there are. Well, there's 2, there's 3, there's 5, and there's 7, right? So 4 is not prime because it's divisible by 2. 6 is not prime because it's divisible by 2 and 3. 8 is not prime because it's divisible by 2 and 4. And 9 is not prime because it's divisible by 3. And 10 is not prime because it's divisible by 2 and 5. So that means that we have 4 prime cards, 2, 3, 5, and 7. And there are 4 of them per suit. There are 4 suits, so a total of 16 out of 52. And then the last thing is that we need to figure out how many odd numbered prime cards there are. So looking at our prime cards, there were 2, 3, 5, and 7. 3 of those were also odd. So that's 3 per suit. So 3 times 4 suits gives us 12 total cards out of 52. So we're going to get 16 plus 16 is going to give us 32, minus 12 is going to give us 20 out of 52, or 10 out of 26, which is 5/13. And then, of course, we figure out what this is a decimal. This would be 20 divided by 52, gives me 0.3846, which I'm going to round to 85. Now let's take a look at problem 19. You're playing a game that takes 2 rounds. In the first round, a 4-sided die is rolled. If an odd number turns up, a weighted coin with a probability of heads of p equals 0.7 is flipped. If an even number shows up, a fair coin is flipped. once the die has been rolled and the coin is flipped, the game ends. So what we're going to do for the first part is we're going to draw a probability tree diagram. So if we look at our outcomes that we're interested in, when we roll a four-sided die, whenever we draw a probability tree diagram, or a tree diagram in general, we start with some starting point, and then we do a branch for every single outcome that we're interested in. Now, if I were looking at the face of the die, and I were marking what it is, 1, 2, 3, or 4, because it's a four-sided die, I would have 4 branches. But in this case, I'm not actually interested in whether I get a 1, 2, 3, or 4. All I'm interested in is the outcome odd, or is it even? And then it says, after this, I'm going to flip a coin. If an odd number turns up, I'm going to flip a weighted coin. So first things first, let's actually get our probabilities here, because we want a probability tree diagram, not just a tree diagram. So I didn't say anything was weighted on this die, so I'm going to assume that all 4 outcomes, 1, 2, 3, and 4, have an equal likelihood of occurring. So therefore, each one has a 0.25, which means that the probability of getting the odds is just 0.25 plus 0.25, or 0.5. And the probability of getting an even number is also 0.5. So once I get my odd number, what I'm going to do is I'm going to flip a coin, and I can get heads or I can get tails. And it says that if I get an odd number, I'm going to flip a weighted coin with a probability of heads of 0.7. So my probability of getting heads is 0.7, then my probability of tails is 0.3. If I get an even number when I rolled my four-sided die, then I'm again going to flip a coin with heads or tails, but this one is a fair coin, meaning that the probability of heads is 0.5 and the probability of tails is 0.5. So now we have our probability tree diagram for this 2-turn game where we're going to roll a die, and if it's odd, we're going to flip a weighted coin, and if it's even, we'll flip a fair coin. The second part of the problem says to find the sample space of this game. So to find the sample space, it's just going to be S equals curly bracket, and then we're going to follow each path. So we have odd heads, then we have odd tails, then we have even heads, and then finally even tails. So these are the 4 possible outcomes for this game. And the last part of the problem says, construct a probability distribution for this game. So a probability distribution, if you remember, is just all the different outcomes and their probabilities. So we need the probability for each of these outcomes. And because we know that this accounts for every possibility from this game, we know that the probabilities have to add up or sum to 1. So first thing I'm going to do is I'm going to get the probability of getting an odd followed by a head. So the way I find this is I just go down the branches and I multiply these probabilities. So this is going to be 0.5 times 0.7, which is going to be equal to, I know what the answer is, but I'm just going to look it up anyway, 0.35, just like we would expect, half of 0.7. And then I'm going to do probability of getting odd followed by tail, which is going to be 0.5 times 0.3. So in this case, half of 0.3, 0.15. Now, if I go down these branches, I need to get even heads and even tails. Well, if I look at this, I'm going to get the same probability for both. So probability of even and heads is 0.5 times 0.5. Probability of even tails, 0.5 times 0.5. So instead of writing it, I could write it, each one of them, just like I did before. Or instead what I'm going to do is I'm going to say that the probability of even followed by heads is equal to the probability of even followed by tails equals 0.5 times 0.5, which is equal to 0.25. Now, one thing I want you to keep in mind, though, is when you're looking at whether these add up to 1, you have to consider that probability of even heads is equal to 0.25, and probability of even tails is also equal to 0.25, meaning that this together is 0.5 plus 0.35 is 0.85 plus 0.15. It does, in fact, add up to 1. Now, one thing I want to kind of caution you about in this part, if you were going to do this for whatever sort of scenario I give you on the test, do not ever write it as the probability of even heads equals even tails. This is not true. So in this case, you actually have written something that is incorrect. Even heads is not the same as even tails. The probability of even heads is equal to the probability of even tails. So you can do this to shortcut it a little bit, especially if you have a lot of things that overlap, but you cannot write it this way. This is incorrect. Number 20 says an urn contains 8 red balls, 4 blue balls, and 3 green balls. So we have 8 red, we have 4 blue, and we have 3 green. A asks us to select a ball randomly. What is the probability that a ball chosen is either red or green? So just like before, we're going to take probability of red or green, which is going to be the probability of getting a red ball, minus the probability of getting a green ball, plus the probability of getting a green ball, minus probability of getting a red and a green ball. So my probability of getting a red ball, what I need to do is I need to take, right, so our probability of any outcome A is just the number of outcomes in A divided by the number of outcomes in the sample space. So in this case, we have a total of 8, 12, 13, 14, 15 total balls, and there are 8 red balls. So this is going to be 8 out of 15. Plus, now we need the probability of our green balls. We have 3 out of 15. And then we need to subtract the probability of getting a ball that is red and green. Now, these outcomes are actually mutually exclusive because a ball cannot be both red and green in this urn, meaning that this is actually the empty set, which means this is going to go to 0. So we get 8 plus 3 is going to be 11 over 15, which is equal to 0.733. Part B says to draw 2 balls in succession without replacement. What is probability that both balls are blue? So we want the probability of getting a blue and a blue. Now for this one, we have to think about the fact that we're drawing 2, but we're drawing them in succession. So what's going to happen is, because this is an and statement or an intersection, this is multiplication. So this is going to be the probability of drawing a blue ball times the probability of drawing a blue ball given that we drew a blue ball. So this is our first blue ball. We draw it, probability of that occurring. If we chose that blue ball for the first turn, what's the probability our second ball is a blue ball? So first things first, what is the probability of drawing a blue ball? Well, there are 4 out of 15. And now we need to figure out what is the probability of drawing a blue ball given that we've taken one out of the urn. So now, because there were 4 blue balls and we took one out, there are now 3. And there's now 1 less total ball in this urn, which means it's out of 14. So this is going to be 4 divided by 15 times 3 divided by 14. So then I just put this in, 4 divided by 15 times 3 divided by 14, and I get a probability of 0.057. So the probability that I would get 2 blue balls in a row with this scenario in this urn is 0.057. Problem 21 says 52% of candidates taking the Actuarial Exam P pass the test. You randomly select 10 Exam P candidates. Question A asks, what is the probability that the number of candidates who passed is exactly 4? So first things first, this is going to be what kind of problem? Well, we're looking at a number of trials, the 10 candidates, and they have 2 possibilities. They either passed or they didn't pass the exam. So this is going to be a binomial problem where I have n equals 10, the number of candidates, and the probability that they pass the exam is equal to 52%, or p equals 0.52, which based on this, that means that the probability that they fail the exam is going to be q equals 0.48. Problem A asked, what is the probability that exactly 4 of our candidates pass this exam? So as before, we're going to be using our binomial probability. Probability of x is n choose x, p to the x, 1 minus p to the n minus x. Now on the exam, if you put q for 1 minus p, that's perfectly fine. If you put your combination as NCR, that's perfectly fine as well. And in fact, you could have also just written this as probability of 4. I'm just trying to be, precise. So plugging this in, we're going to get 10 choose 4, 0.52 to the 4th power, and then the probability of failure, which is 0.48 to the 10 minus 4 power, or 6th power. So plugging this in, first things first, let's figure out what 10 choose 4 is. So 10 choose 4, I get 210. So 210 times 0.52 to the 4th power times 0.48 to the 6th power. 210 times 0.52 to the fourth times 0.48 to the sixth, and I get a probability of 0.1877, so I'm going to round this to 1.88. Part B says, what is the probability that the number of candidates who pass is at least 8? So the probability of at least 8 means that it is greater than or equal to 8. So greater than or equal to 8. And solving this, this would be the probability of getting 8 that pass, plus the probability of getting 9 that pass, plus the probability of getting 10 that pass. So what we'll do is each of these, we will just use our binomial probability formula and we will solve for them. So this is going to be 10 choose 8 times 0.52 to the 8th power times 0.48 to the 2nd power plus 10 choose 9, 0.52 to the 9th power, 0.48 to the 1st power, plus 10 choose 10, 0.52 to the 10th power times 0.48 to the 0 power. Now, just like when we were doing our binomial problems earlier, this follows a certain pattern. 10 choose 10. If I have 10 objects and I want to pick all of them, how many ways can I do it? Just one. 10 choose 9, right? So n choose n is always equal to 1. N choose n minus 1 will always be equal to n, right? Because if I have 10 candidates to choose from, how many ways can I choose 9 of them? Well, let's rework that problem a little bit. How many ways can I not choose one of them? Well, I could not pick the first candidate, or not pick the second, or not pick the third, up to the 10th. So this one is going to be equal to n, which in this case is 10. So for this probability, this one's going to be pretty easy because it's 1, and then 0.48 to the 0 power is also 1. This is just 0.52 to the 10th power, which is going to be 0.001445. I'm just going to leave a ton of extra decimals so that we'll round at the end. For this one, it's going to be 10 times 0.52 to the 9th power times 0.48. So I'm going to do 10 times 0.48 times 0.52 to the 9th power. And I'm going to get this one is equal to 0.013345. And now we need to do this last one. So 10 choose 8 is going to be 45, which again, I'm going to do this by hand also, just in case anyone wants to see how we do it. So this is going to be 10 factorial divided by 10 minus 8 factorial, 8 factorial. 10 minus 8 factorial is just going to be 2 factorial. So what I'm going to do is for the denominator, I'm going to bring the largest factorial over. So this is going to be 8 factorial. And then the other factorial, I'm just going to write it out. So this is going to be 2 times 1. The 1 doesn't do anything. Now for the numerator, I'm going to take this and I'm going to take my factorial until I get to the size of this largest factorial in the bottom. So I have 10 times 9 times 8 factorial. Now my 8 factorials cancel. This 2 cancels with part of the 10, leaving me 5 times 9, which is equal to 45. So we have that now. So 45 times 0.52 to the 8th power times 0.48 squared. So let's plug it in. We get 45 times 0.52 to the 8th power times 0.48 squared is going to give me 0.055427. Adding these all up together now, I have 0.055427 plus 0.013345 plus 0.00144555 is going to give me 0.0702165, which I'm going to round to 0.070. So the probability of having at least 8 candidates pass is only going to be about 7% chance of happening. Now, part C of this problem says, what is probability that the number of candidates who pass is less than 2? So same idea, we're going to take the probability that we have less than 2. Now, because this is discrete data, this is the same thing as saying, what is the probability that I have less than or equal to 1? So I'm going to be finding the probability that none of the candidates pass plus the probability that one of the candidates pass. So So just like before, I'm going to plug in my values. This is going to be 10 choose 0, 0.52 to the 0 power, 0.48 to the 10th power, plus 10 choose 1, 0.52 to the 1, 0.48 to the 9th power. And then, of course, plugging in each of these values, again, 10 choose 0 is going to be 1, 10 choose 10, or 10 choose 1 is going to be 10, 0.5 to the 0 is going to be equal to 1. This one's just 0.48 to the 10th power, which is going to be equal to 0.0000, oh, sorry, 3 zeros, 0.00064925. Plus, this is going to be 10 times 0.52 times 0.48 to the 9th power, and I get 0.0070335. And I did this because generally on the form it says to use 3 decimals, but really and I kind of explained this in class, we're more interested in significant figures, right? Because if I just did this to 3 decimals, this would be 0.001, 0.001. But what if we had like one more zero? Sometimes it would cause us to say it's 0. So unless it's a ton of zeros, just do significant figures, just because some of these problems will have very small probabilities. So adding these together, we get 0.000064925 plus 0.0070335. And this will give me 0.0076825, which, of course, if we just rounded it like I talked about, this would be 0.008. For our next problem, it says, in a space exploration board game, players are tasked to take on missions of varying degrees of difficulty. The data below represents the success rate of players based on the level of hostility on a game's planet and the experience level of the players. So looking at our table, we have planets that are hostile, neutral, friendly. We have ability of the players, novice, intermediate, and expert. And then anywhere the cells intersect, that would be how many players that are novices were able to succeed. For example, 12 players that were novices were able to succeed on a hostile planet. 21 players that were intermediate were able to win on a hostile planet. 39 players who were expert were able to win on a hostile planet, for a total of 72 people who were able to win the game on a hostile planet. I will admit this is not one of my better problems I've made in the past. This was actually a prior test question because one of the questions is a little bit ambiguous, and I had some students argue about it because the wording wasn't as precise as it should be, and I ended up giving credit for both approaches, but I'll tell you what the idea of the problem was. So the first problem asks, what is the probability that a randomly selected planet selected is neutral? So in this case, the first one is just looking for what is the probability of picking a neutral planet. I'm going to put this as NE for neutral. So the probability of selecting a neutral planet is that we have 132 neutral planets, right? Because I'm just taking the number of neutral planets divided by the number of our entire sample space, which is 313. So my neutral planets are 132 out of 313, which is equal to a probability of 0.4217, so 0.421. Question B asks, what is the probability that a randomly selected player is a novice? So same idea. What's the probability of selecting a novice? It's just the number of novice players over the number of all players that were able to succeed in a planet. So if we go into novice, we go to the total, we have a total of 74 novice players out of, again, a total of 313 players that were successful. So this would be 74 divided by 313, which is going to be equal to 0.2364. Part C asked, what is the probability of success for an expert player on a neutral planet? Now, this was one where there was some confusion because what I meant by this was basically I just wanted expert and neutral. What is probability in a game that an expert player is successful on a neutral planet? But it was that term of the successful part instead of just saying what is probability of picking an expert player and a neutral planet. So this one is supposed to be probability of expert and neutral, which we know from our intersection, right? Our and probability. This is going to be multiplication. So this is going to be the probability of picking an expert player times the probability of getting a neutral planet given that we have an expert player. Or you could do the probability of a neutral planet times probability of an expert player given a neutral planet. But realistically, we actually don't need to do this method because we have this contingency table. Because we can use our basic form of probability, which is just the number of expert and neutral planet divided by the number of our sample space. Because we can actually look this up. We know how many expert and neutral planet successes there were, 52. So this is just going to be 52 out of the 313, which is going to give us 0.1661. Question D is, what is the probability of success of an intermediate player given a friendly planet? So we want the probability of an intermediate player given a friendly planet. So remember, whenever we have a contingency table, what we're going to do is we're only interested in the friendly part. So really what we're looking for is we are looking for the number of intermediate and friendly divided by the number of friendly, because this is a conditional probability. But for the table, as soon as you see that given friendly, you only care about this column. So how many are intermediate players? 38 out of how many players total on a friendly planet? 109. So this would be 38 over 109. And we get a probability of 0.3486. And then for the last question on this part, what is the probability of success if a player is a novice or a hostile planet was selected? So we have the probability of a novice or hostile planet. So this is just going to be the probability of a novice player plus the probability of a hostile planet minus the probability of a novice and hostile planet. So if we looked at novice, we have 74 out of 313. Plus, if we look at probability of a hostile planet, we have 72 out of 313. And then minus the probability of novice and hostile planet, which is going to be 12 of them out of 313. So 74 plus 72 minus 12, so really 74 plus 60 divided by 313. So 74 plus 60 would be 134, which is going to give me a probability of 0.4281. Problem 23 says the Pew Research Center reported that approximately 30% of U.S. adults own a tablet computer. Suppose a simple random sample of 15 people was taken. Part A, find the probability that exactly 4 of the sampled people own a tablet. So in this case, this is also, again, going to be a binomial probability problem because we're selecting n equals 15 people, and each of them have a probability of success, in this case, of owning a tablet, which is going to be p equals 30% or 0.3. So of course, the probability that they don't own a tablet is going to be 0.7. So the first question asked us to find the probability of exactly 4 sampled people owning a tablet computer. So we just want the probability that x equals 4. So of course, I'm going to write down my probability again because we always need to show what formula we're using. So this p to the x, and then I'm just going to do q to the n minus x for this one. So I'm going to plug in my values. This is going to be 15, choose 4. Then probability of success, 0.3 to the 4th power. Probability of failure, 0.7 to the 15 minus 4, or 11th power. So plugging this in, 15 choose 4 is going to be 1,365. So that's going to be that value there. So I have 1,365 times 0.3 to the 4th power times 0.7 to the 11th power, and I get a probability of 0.2186. Part B asks us to find the probability that fewer than 3 people own a tablet computer. So just like before, probability x is less than 3 is the same thing as saying probability x is less than or equal to 2, which is equal to the probability of 0 people owning a tablet from our sample, plus probability of 1 person owning a tablet from our sample, plus the probability of 2 people owning a tablet from our sample. So this is going to be equal to 15 choose 0, 0.3 to the 0, 0.7 to the 15, plus 15 choose 1, 0.3 to the 1, 0.7 to the 14, plus 15 choose 2, 0.3 to the second power, 0.7 to the 13th power. So again, this is 1, this is 1, this is going to be 0.7 to the 15th power, which is going to be 0.00474756. I'm just going to round to 6. Plus 15 choose 1 is going to be 15. So 15 times 0.3 times 0.7 to the 14th power. This is going to be 0.03052,003 plus, now 15 choose 2 is going to be 105. So 105 times 0.3 squared times 0.7 to the 13th power is going to give me a probability of 0.09156001. So adding these all up together, I get a total of 0.0474776 plus 0.03052003 plus 0.09156001, and I get a total of 0.12682. So I'm just going to round this to 0.1268. I'm doing 4 decimal places. If you were doing 3 decimal places like on the exam, then this would just round to 0.127. And the last question on this asks us to find the probability that more than 1 person owns a tablet computer. So this wants the probability that x is greater than 1. Now, if we were to find this, this is equal to the probability that x is greater than or equal to 2. So this means that if we were going to try to brute force this, we would have to find the probability of 2 people having a tablet computer, plus probability of 3, plus probability of 4, up to the probability of 15. Now, I would never ask you to do this many binomial calculations for one problem worth 5 points on an exam. So then you should ask yourself, is there a trick which I can actually do in order to not have to do this many binomial probabilities? And the answer is yes. I'm actually going to take the fact that if I take all the probabilities summed up together, I know that they're equal to 1. So if I take the complement of this, which the complement of probability of x is greater than 2 is going to be the probability that x is less than 2, and I'm going to subtract that from 1. Now, of course, again, we can't find the probability x is less than 2, so what we're actually going to find is we're going to find 1 minus the probability x is less than or equal to 1, which is going to be 1 minus the probability of 0 plus the probability of 1. Now, thankfully, we actually already have these values from the first set of calculations we did, or the last set of calculations we did. The probability of 0 people owning a tablet computer is 0.0047476. The probability of only 1 person from our sample having a tablet computer is 0.03052,003. So then I'm just going to take 1 minus, and then 0.0047476 plus 0.03052,003. So I'm going to figure out what this value is, subtract it from 1, and I'm going to get a probability of, so 1 minus 0.0047476 minus 0.03052,003. By the way, if you're doing this on your calculator, be careful because you need to distribute this negative, or you need to first figure out what this value is and then subtract it from 1. The most common mistake I see students make here when they're doing this is they will subtract, they'll do 1 minus and they'll do this value, but then they just do plus this. And if you don't have parentheses, that's going to be incorrect. So I get a probability of 0.9647. So that's the probability that more than one person owns a tablet computer. 96.47% of the chance of that happening. Now I want to do one more bonus problem that isn't on this review. And it's because I noticed we didn't put any combination problems, even though that is part of the material that we might cover. So let's say, for example, that we have a committee made up of, or we have a group of 3 physics majors, 4 chemistry majors, 4 biology majors, and 2 math majors. And we want to make a committee of, 7 people to represent these departments. So what we want to do is we want to know the probability of getting a committee made up of 2 physics majors and 2 chemistry majors and 2 biology and 1 math. Let's say that's what we want to know what the probability is. I'm just making this up on the spot. So the way we would find this is we're actually going to be using combinations, because what we're going to do in this case is we need to figure out how can we choose from these 3 physics majors, how can we choose 2 of them? So this is going to be just the number of ways that I can get 2 physics and 2 chemistry and 2 biology and 1 math major out of the total number of ways that I can make a 2, 4, 6, 7 person committee. Which, remember, committee means that there is no ordering to this, right? It's not president, vice president, treasurer, stuff like that. It's literally just they're a committee of 7 people of equals, which are going to represent the STEM majors for this university, let's say. So first things first, we need to figure out how many ways can I get 2 physics, can I choose 2 of the physics majors out of the 3? How many ways then can I find 2 chemistry out of the 4 chemistry majors? How many ways can I pick the 2 biology majors from the 4 biology majors? And how many ways can I pick 1 math major from the 2 math majors that I can select from? So this is going to be equal to 3 choose 2 times, because this is an and, right? And means multiply. And then 4 choose 2 times, again, 4 choose 2 times 2 choose 1. Divided by, now we need to figure out how many ways can I make a 7-person committee. So I'm going to be choosing 7. Now I have to figure out how many people I have total. So 3 plus 4 is 7, it's 11. I have 13 people that I'm choosing from, and I'm going to pick 7 of them. So 13 choose 7. So if we were then to do these different numbers, we have 3 choose 2. Now I could put this in my calculator, right? I could say, what is 3 choose 2? And I would get 3. But if you remember your patterns, this is n minus 1. So n choose n minus 1. So 3 choose 3 minus 1, which is 2, will always be n. So this is going to be 3. Oops, times. Then we have 4 choose 2. So we go 4 choose 2, and we'll get a total of 6 ways that we can select from our chemistry majors and select 2 of them. Same thing, we have 4 biology majors, we're choosing 2 of them, so this is going to be times 6. And then we have 2 math majors, where how many ways can we choose just 1 of them? There's 2. We can pick the first one or the second one. So we have 3 times 6 times 6 times 2, divided by how many ways can we pick a 7-person committee out of the total of 13 people? So we go 13 choose 7, and we get 1,716. So the probability of getting a committee made up of 2 physics majors, 2 chemistry majors, 2 biology majors, and 1 math major is 3 times 6 times 6 times 2 divided by 1,716. So 3 times 6 times 6 times 2, which is just going to be equal to 216 over 1,716, which would give us a probability of 0.12587. So let's just say 6. So in this case, this means that there's only a 12.6% chance that this committee, made up of 2 physics majors, 2 chemistry majors, 2 biology majors, and 1 math major, would happen, given that we have 3 physics majors to choose from, 4 chemistry, 4 biology, and 3 math. And any of these kind of combination problems will be like this, right? You have so many things you can choose from. How many ways are you selecting from it? So you're having some sample of size R. And then you just have to figure out, if you're taking some committee made up of this and this and this, you're going to multiply out the number of ways I can do it. And then you're going to divide by how big of a committee you're making out of your total number of people. So those are some of the examples for all the different topics that may be on the upcoming exam. And hopefully with this, it'll help you kind of prepare for it, knowing that this is going to be very similar to the kind of stuff we're going to ask, but it's going to vary a little bit from there. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.